Hi, and welcome to Introduction to Systems Programming. Today I will be talking about what is systems programming and why do we need it, and also why is it necessary to first have an introduction before we delve deeper into the issues related to systems programming. In my experience, a lot of talented programmers and software developers are kind of not very aware of the issues that surround systems programming. And when it comes to actually building systems, uh, people usually lack experience or insight. So I thought it's very important at this point to think about the issues that are critical when building systems so that we could actually make a reliable system in the presence of errors. So you will see in this presentation that we will be talking a lot about errors, what they are, how do we deal with those, and the reason we are emphasizing that aspect of software engineering is mostly because a lot of software engineers and computer programmers or software developers tend to approach the um, construction of software and computer programs in a very optimistic way, meaning they are assuming that most of the time all the aspects of the information processing will be fully functional, and starting from that assumption, then they implement the business logic and the processing code that sometimes is really incapable of dealing with various issues and roadblocks that pop up. So in this presentation, we will be looking at some of the most typical issues that will um, probably become a hurdle or a roadblock and sometimes even a blind alley, and also talk about how do we avoid those pitfalls. Let's first look into what is a system before we talk about how do we deal with issues and errors that are plaguing the system. The system is something that stands together and composed of programs that offer services to other programs. So it's a constellation of software programs without any global supervision or managers to overlook those services and how they interact. Therefore, the programs and services are loosely coupled. If they're tightly coupled, then it's not really a system, it's more like a monolith. We'll talk about that a bit later. Everything that we build, it will eventually exceed our ability to understand it. So this is the complexity that is the essential characteristics of any sufficiently large software system. Uh, at first, when we are at the early stages of building a system, we can keep everything in our heads or on a diagram, but eventually gets to a point where it just exceeds our ability to understand what it is. So a diagram may illustrate this, where on the x-axis we have plotted complexity from left to right, which basically boils down to number of moving parts. As the number of moving parts increases, the randomness or the degree of independence increases along the y-axis. Our formal analysis is only good at the very early stages, which is this kind of lower left-hand corner, where the formal analysis can help us deal with the system. However, as the complexity or the number of moving parts increases while the degree of independence, meaning randomness, also increases, we get to the point where our formal analysis fails and our system could be tackled only via something that we call statistical analysis. And as you can see on this chart, the statistical analysis pales as we are increasing the number of moving parts. So in between the formal analysis and the statistical analysis, there is a gap. And this gap is counterintuitive, and just because we cannot grok it, either by using formal analysis or statistical analysis, doesn't mean that we can safely afford to ignore that gap. And the the intention of this presentation is to address this gap and see if we can somehow deal with it instead of just sweeping under the rug, face it head on, and see what we can do about handling that gap. Because as we're building systems, as we are adding number of moving parts, and also we are keeping these things independent of each other, meaning we are increasing randomness, we need to be able to manage and control and avoid the system disasters or crashes. And of course, first thing that comes to mind when we're saying, okay, now we need to control the system, so which system language do we use? What is the system language? Same as when we're building software, we're using programming languages of various kinds. What is a system language? And the answer is that such thing does not exist. And this is the problem, because we do not have a system language that we could use to manage and control our system. If we look at a program talking to another program, which is what a number of programs talking to a number of other programs, we need to ask, how is this happening? And of course, the answer is it's happening over the network, which are inherently unreliable, as we all know. So errors that we're concerned about are at the system level. For example, if one of the programs that are comprising the system becomes all of a sudden unavailable, this is the error, because we are counting on that program, on that service to be available. This has nothing to do with programming errors, because programming errors are not really errors that we're talking about here. They are basically just bugs to be squished. And even when we squish those bugs, it doesn't mean that we have eliminated those errors. So bugs are separate from errors. And of course, as the old adage goes, a chain is only as strong as its weakest link. So even if everything else in our system is rock solid, if there's one part that it's failing, then this whole chain fails. And this brings us to the question that is crucial to be able to effectively manage the system, which is how to provide an abstraction boundary which stops the propagation of errors. So we need to be able to detect the arrival of an error or the occurrence, and then be able to stop it, not let it propagate. And this is something that we call abstraction boundary. Let's look at how programs talk to each other. They talk by using protocols and formats. In the old days, and I call that historic epic failures, we had several attempts to build those protocols. One is the old school remote method invocation, which is used in Java, RMI, where we are demarshalling and marshalling and demarshalling Java objects across the wire. Another one is another epic failure was CORBA, or Common Object Request Broker, which didn't go anywhere. Also, Microsoft had their version called DCOM. All these things are they happened during the object infatuation phase, the so-called object infatuation phase, which happened back in the 1990s, where object-oriented became mainstream. And we're hoping this will never happen again, because it was very, very unwieldy, very clunky, and it didn't work. And we had to adapt. And today we are finally over this object fetishizing, and we're back to focusing on getting things done instead of being obsessed about object hierarchies and etc. So what's happening today? Instead of objects, today we are learning that it is very useful to to focus on values. And I'll try and explain why. So the value of values, they're very, very valuable in system programming. So values are good because they have no identity. For example, a value such as the number 42, which always gets used in these technical discussions, that number has no identity. It's just a value. And also, values are mostly ephemeral. They're short-lived. They don't need to be, we don't need to hold on to the values. We don't have to store them anywhere and take care of them and worry about them. They're just for the time being. Also, they're nameless. We don't have to worry about coming up with a meaningful name. And they're on wire. They're not stored somewhere in a location in the computer memory. They're just happening on wire, ephemerally being schlepped across the wire. So for example, if there's a service that returns monthly payment rate on a term loan, so say somebody has a term loan and monthly payment is $500. That value is $500. It is ephemeral because it may change. It needs no name, it's just a value, and it's probably traveling across the wire from one node to another. And this ephemeral nature of values implies flow, so things are flowing. Which brings us to the crucial point to keep in mind that systems are not place-oriented. It is not something that has its particular address and place and it happens there. Rather, systems are flow-oriented. They're flowing and they don't have fixed address. They're flowing from one node to another, and that's how things are getting done inside the system. Like so, an example from real life would be the assembly line in the car factory, where cars are not being, an individual automobile is not being assembled in a single location where they kind of start building it and until it's completely done, it doesn't leave any particular spot. The automobile is flowing through the assembly line, so it's moving, and with each step, certain things are being added to it, so it's slowly being assembled until it finally is a full-blown, fully functional automobile. So this assembly line flow analogy is very important to understand software systems because they're exactly built on the same principle. It's the assembly line, it's the flow. Now the question is, of course, we are all intuitively very clear on how do half-baked cars flow through the assembly line until they fully materialize into an automobile that somebody can buy. And how do values now flow in the system? Because values are more abstract, of course. And basically there is 4 steps or 4 aspects. There is a transformation aspect of the value. So value gets transformed, then it moves. It's not fixed location. There's a routing. Records are being kept, logs of the particular fact. So certain events are being recorded and become facts, and they're immutable. And also all these activities, all 4 activities, transform, move, route, and record, are kept segregated. They are segregated. Let's look at this transform, which we're using the symbol lambda from the functional programming, the transformation of values. We will not dwell on it because it's very clear what it means. The move aspect of the value flow through the system is, of course, we have a source and we have a destination. The producer, the mover. Now we know that it depends on identity and availability. So we must decouple movers, producers from consumers. The dependency on identity is undesirable, must be removed. Also, the dependency on availability is not desirable, so it must be removed. How do we do that? How do we decouple producers from consumers? Simply, the most useful way is to use queues. So instead of directly communicating between producer and consumer, we have an intermediate brokerage layer, something that allows producers to publish their changes or the values, and consumers can then use that mechanism to subscribe and be notified when a new transformed value is published. Another thing that is very important for people who are trying to build systems is that when designing services, we typically, we are trained to design services to be consumed by human users. But in systems programming, it is crucial to design services primarily for machines. I will explain what that means. We need to avoid designing services to be consumed by humans. Machines, when they talk to each other, should never be expected to access services via the operational interfaces, because operational interfaces are designed for human use. And for example, today, if we have a machine or a system that needs to access a service such as Git, then all bets are off, because Git was built from ground up with an operational interface to serve human needs, and it is completely opaque and very complicated and convoluted for machines to use it, because Git is it's more like a chatbot that tries to implement some kind of a common sense and human intuitive approach to requesting services. Therefore, machines are out of luck with Git. So Git is an example of a system or a service that is not very well behaved in sort of the world of system programming. Of course, we're not saying don't build human operational interfaces, but the point is build them only after you've built a machine-centric service, not before, because that approach will guide and will be very beneficial for the sake of the system. And it is easy after the fact to bolt on some kind of a human operational interface, but the other way around doesn't work. If we build a human-centric operational interface, then trying to bolt on a machine-centric interface is not that easy. So when we are building services and trying to build components and parts of our system, it's very important to strive to build only simple services. Because simple services are easily composable. If a service is not simple, if it has complex surface, then when we are trying to compose it, use it as a part and compose something bigger, it is very, very tough to understand how will that complex surface fit into a brand new, unpredictable environment. But if the surface is very simple, very kind of has only maybe one contact point, then it's easy. It's like a Lego block. It's just like, okay, here's a contact point, and you can plug it in, and by using many of those simple, small components or services or parts, we can repurpose them and build a larger structure that when we were building our basic structure, we didn't even anticipate. So the idea for that is to remain future-proof, so that when we build a service, it can be later on repurposed and put in another situation, in another context, and be still functional and useful, even though we never anticipated such use for it. When we are designing simple services, then we are not in danger of doing what's called premature abstraction. This is potentially, a very slippery slope when we're doing premature abstraction and we are trying to anticipate something, because we are assuming a lot of things that may or may not happen. With simple services, there is no room for assumption. There is no room for us to kind of think about, what if this and that happen in the future? We are just addressing the very simple problem area. We solve it, and it has a very flat, simple-minded surface area, and it could be easily plugged into some other future situation that we could not anticipate. So there is no premature abstraction. And again, we cannot over abstract a simple service. It's not possible. If we don't know, if we're not sure whether we are really building a simple service and whether we are prematurely doing premature abstraction, it is a good practice. It's very advisable to consider a second implementation of your service interface. And what that means is, let's say you start designing your service by abstracting it using HTTP protocols. So say, all right, this service I'm building is going to actually be responding to HTTP requests and will be responding with HTTP responses and some kind of a status code. So that all looks pretty straightforward and easy. But we should also at that point consider offering the exact same service via some different protocol, such as SMTP. So that's interesting because through that exercise, we will be able to sort out our abstractions. And maybe we will realize, oh, wait a minute, while it looks easy to implement this service using this protocol, when I switch over to that protocol, I realize, oh, this is actually tightly coupled to something else, so it doesn't work. That helps us, puts pressure on our design and helps us architect our system better. The biggest challenge and the most important thing is to avoid turning your service into a monolith. I'll explain what that means. We should abstain from adding functionality and features. Just because we can easily add some functionality and some features, we shouldn't knee-jerk just jump at it. We need to keep ourselves, self-restraint is very important here. We need to keep our approach super simple. Yes, it is often easy to just throw in some extra bells and whistles, some new features, very, very interesting, very potentially useful. Try and keep abstain from that. Try and keep yourself restrained, because that is not easy to do, and that is a tough approach, but it pays handsome dividends down the road, because now you're building a system component or part that is easily composable and, as we'll see later, much more easier to manage. So another thing is to avoid at all cost is to turn your service into a stack. Stack is evil, it's bad, and it's always going to come back to bite us. I'm always on the lookout that we should never end up with a stack. So instead of building a stack, we should allow users of the service to choose their commodity, whichever commodities they prefer when consuming our service. So it is their choice, not ours. Meaning we let them decide which data store to use, which queues to use, etc., etc. We are not going to, it's not good to dictate our custom stack to our clients. That is always a bad smell, a bad sign when somebody's saying, oh yeah, well, in order to use this service, you need to be able to also front load, this and that, the other. That's not good. So moving on from this kind of orientation into the topic of failures, which, as I mentioned at the beginning, systems are implemented on computer networks, which are inherently unreliable, so failures are fact of life here. So system failure model, basically, for our purposes, is the only failure model. Because system failures are guaranteed to happen. That's the fact of life. It's not if they're going to happen, but more like we are considering when are system failures going to happen and how often are they going to happen. So we have exceptions on the system. They occur when the runtime system runs into a situation, doesn't know what to do. Then the runtime system is faced with an exception. We have errors on the other hand, and they happen when the programmer runs into a situation and doesn't know what to do. So there's a difference between exception and error. System failures are always partial. They're uncoordinated. They happen in some part of the system because it is extremely unlikely that the entire system fails at once. That's just very, very unlikely. And that is something that nobody can recover from, but it's not something we can even consider. So what are the minimum requirements for reliable systems? Because here we're talking about how do we build reliable systems in the face of inevitable errors. So first of all, reliable systems must be built to handle concurrency from the ground up. Concurrency is not an afterthought. And in order to do that, the system must be non-imperative. It should not do things sequentially in an imperative fashion, but more like as a process, because everything is a process. And in real life, there's no situation when all other processes are waiting for that particular one to finish and then they jump in and continue. Because same as in any other situation, things are happening in parallel. If we're driving on a highway, it's not like one single lane, single file cars. Cars are merging and entering and leaving, off ramp, on ramp, etc. So everything is a process. So we need a lightweight mechanism for creating parallel processes. That is the kind of most fundamental condition. If we are to build reliable systems, we cannot do so unless we have already a way to build and create parallel processes, and this way should be lightweight, not very costly. Also, we need an efficient context switching between processes and messaging passing. We need to be able to have fault detection primitives because that will allow us to observe from one process to observe another process through these fault detection primitives. The error encapsulation is important because errors occurring in one process must not be able to damage other processes in the system. So we need this abstraction boundary that we talked about before. And Jim Gray says that the process achieves fault containment by sharing no state with other processes. Its only contact with other processes is via messages carried by a kernel message system. So again, not a monolith, complete isolation, and no sharing of any state. Just communicate with other processes via messages. And Jim Gray continues, as with hardware, the key to software fault tolerance is to hierarchically decompose large systems into modules, and each module being a unit of service and a unit of failure. It's very important, a unit of failure. A failure of a module does not propagate beyond the module. This is the ultimate isolation. So we need fault tolerance, and we achieve it by decomposing large systems into smaller modules and then encapsulating a failure within a single unit. That way, these are the abstraction boundaries that prevent failure to propagate beyond. This now brings us to another very important topic, which is when writing implementation code, we should have it in such a way that it only handles the normal case, not the exceptions, not the oddball cases, not the side effects. But if there's a specification that is described as something that is expected the system should do, then the implementation code handles that. It focuses on the so-called normal case. Otherwise, let it crash. This is the let it crash philosophy, which some people find maybe counterintuitive or a little bit of startling or astonishing, but there is a reason for it. It's also very important not to try to fix up the error when it occurs and then continue. Our code should not be trying to recover and like, oh no, I'm okay, I handle this error, I'll continue processing. No, we basically, any errors should be handled in a different process, not in the one that encountered the error. So this clean separation of error recovery code from normal case code ends up in greatly simplifying overall system design. This is crucial. This is very important. Never mix error recovery code with a normal case code. They should not coexist. They should be completely separate and blissfully ignorant of each other. The fault detection should be capable, should be available both locally. So when there's an exception inside the process, it should be detected, but also should be available to be detected remotely. If an exception happens in a non-local process, somehow another process that has no exception should be able to be notified and to say, oh, I see there was an exception elsewhere. A component is considered faulty once its behavior is no longer consistent with specification. So if we have specification, which is basically declared expectations, here's what we expect this thing to do, and it does it, and all of a sudden it does something differently, then it's faulty for whatever reason. It doesn't matter why its behavior changed, it is considered faulty. And so this now error detection must kick in because it's an essential component of fault tolerance. As soon as the component starts behaving differently than what is expected, this is now an error that needs to be detected. Therefore, we are now building a system that is fault tolerant. If we cannot do what we want to do, so as a system, we are attempting to provide certain service, and for some reason there is an error or a fault, we cannot do it, then we need to drop down one notch lower and try and do something simpler. So we tried that, it didn't work. Okay, let me try something simpler. Because the likelihood of success increases as the tasks become simpler and simpler. Eventually it gets to a point where a super simple task has very large chances of succeeding. But if we have a tricky situation or a challenging situation, those more fancier tasks may be harder to accomplish. And in the face of failure, we become more interested in protecting the system against damage than we are in offering full service. So optimistically, when everything seems to be working fine, there's no failure, of course, we want our best intentions to offer full service and to the customer satisfaction. But then when we detect failure, and depending on how serious the failure is, we get to the point where we're trying to do something simpler, still there's a failure. We may get to the point where we just want to protect our system. We don't want to have a damage occur. And usually the damage in this case means corrupt state, corrupt data. And for the time being, we will discontinue the service just to protect the very core of the system, so the system is not in a faulty or corrupt state. Our goal is to offer an acceptable level of service, of course, but we may become less ambitious when things start to fail. We get to a point and say, okay, that's at this point we need to compromise the service. We need to delay or schedule for later because we don't want to create a incorrect behavior, because that is the biggest damage. We also need a stable error log. So even in the case of a worst crash and everything stopped functioning, we need forensics. We need reliable forensics to go and examine what happened. So the stable error log is critical. So to summarize in 2 steps, step number 1, try to perform a task. Step number 2, if you cannot perform the task, then try to perform a simpler task. So it's very straightforward. This is the gospel of systems program. The fault identification means that when an exception occurred, we need to be able to identify, to see why it has occurred. And again, we need some kind of forensics to be able to play the detective and figure out what caused this exception. Also, at that point, we may detect something needs to change on our system. We need to upgrade the code. But our system is fault tolerant and resilient if it is capable of changing its code while it's already executing and running. So stopping the system is not very desirable. It's only the worst case scenario. So we must strive to have the system up and running and then be able to swap modules, etc., without corrupting the system. That's a considerable challenge, but it's doable. We also need stable storage. The data must be stored in a manner which survives system crash. Goes without saying. So overall, when we think about well-behaved programs, what do we say? The most important, basically fundamental thing about programs is that a program should be isomorphic to the specification. So what does that mean, isomorphic to the specification? Basically, if the specification says something silly, then the program should do something silly. Meaning the program must faithfully reproduce any errors in the specification. So when the errors, later on we realize there are errors, first the specification changes upstream from the program, then the program gets modified and then gets swapped, hot swapped while the system is running. This is the isomorphic aspect of the system programming. If the specification doesn't say what to do, which often that's the case, we just raise an exception. We are not to do any guesswork because this is not the time to be creative. We should stick to the letter of the law. For us, the specification is upstream from our system. We just blindly stick to it. If there is a fault, the specification needs to be changed, modified first, and then it trickles downstream. So this quote here, which says that it is essential for security to be able to isolate mistrusting programs from one another and to protect the host platform from such programs. Again, isolation. This isolation is difficult in object-oriented systems because objects can easily become aliased, meaning at least two other objects hold a reference to an object, which makes it very difficult to isolate and also to hot swap the modules as the system is running. So the writing is on the wall. Object-oriented systems are not the best approach to building fault-tolerant systems. Also, tasks cannot directly share objects. That's why the RMI and all the other protocols failed miserably. The only way for tasks to communicate is to use standard copying communication mechanisms. So no shared state, no shared objects, just messages back and forth. The conclusion to this discussion is that processes are the units of error encapsulation. So our focus is, when we are trying to build a fault-tolerant system, we are cognizant and very focused on errors, and each error, as we identified, must get encapsulated, which means there is a strong isolation within the system. Processes do what they're supposed to do, according to specification, or fail as soon as possible if something happens or the specification did not declare that expectation, so we don't know what to do, we just fail. This is called fail fast, or let it crash. Allowing components to crash and then restart leads to a simpler fault model and more reliable code. So the code is not trying to be very smart, it's not trying to handle some surprises while it's running. It just capitulates. Just throw the towel in, crash, restart, and see what happens next. Failure and the reason for failure must be detectable by remote processes. We already said that. So that processes must share no state and just communicate by message passing. This is just recapitulating what we kind of already talked about. And in case you were wondering, yes, we are talking about process-oriented development. So it's not object-oriented or this and that oriented. It is first and foremost focuses on the process, on the assembly line, on the flow, on not sharing any state or any objects or anything like that, but just sending messages back and forth. And typically via some intermediate third-party impartial service such as a message queue, publish, subscribe service, etc. So that is it for now. Just a short introduction to get people oriented and to raise awareness that while someone could be a very talented software developer, software engineer, and still not be able to face challenges that are of a different kind, where we're trying to build fault-tolerant systems. And just because the code that somebody creates is very uh, well crafted and very skilled, doesn't mean it necessarily can be part of partake in building a fault-tolerant system, which is a completely different kettle of fish. And for questions and inquiries, please send us email to Digital Expert or maybe follow our blog. We will try and get more specific details with hands-on examples, but for now, this introduction is, I hope, useful to people who are getting into a more serious professional software development projects to make sure that the sort of naive and optimistic approach now matures into a more cautious and more, I don't want to say pessimistic, but realistic, being real about what does it mean to have a full-blown fault-tolerant system that can handle all kinds of surprises and unexpected challenges and errors. Thank you very much, and until next time, uh, have fun and continue building amazing systems. Bye.